Okay, we're going to start talking about moving fluids. Up until now, they've been static, and the rules change a little bit if the fluid is moving. We're going to start out by considering a pipe which is wide at one end and narrower at the other end. Okay? And the idea here is that the volume flow rate, and you find that volume flow rate is equal to volume divided by time, is constant. Okay? Whatever volume is coming in the wider end, has to equal the volume that's going out the other end. Okay, if I have 3 gallons per second coming in on the left end, 3 gallons per second has to come out on the other end. Now, if I was to draw this, right, let's say I have this 3 gallons here, and that's how far that 3 gallons moves in 1 second. All right. In order for the volume to be the same, it has to cover a lot larger distance in 1 second. Now, if it covers more distance, it's going faster. So it's faster where it's narrower. And we know this, that's how like a nozzle on a hose works. Or if you have a hose that's spraying water, it doesn't have a nozzle at the end of it. If you want the water to spray out of there faster, you kind of put your thumb over it. What you're doing is you're making the opening narrower. If it's narrower, it's going to shoot out faster. The equation of continuity is that A1V1 is A2V2. You have to be careful, those are lowercase v's for velocity, not big V's for volume. I'm going to make a note over here, because it never says this anywhere, but the volume flow rate whenever it's rate, it means divide by time, so that equals V over T equals A times velocity. They never say that anywhere on the reference table, but it's something that's kind of good to know. This equation is on the reference table, but sometimes they'll ask you for the volume flow rate, and nowhere does it say that AV equals the volume flow rate. Now, here's an example. Fire hose has a radius of 2 centimeters and a nozzle with a radius of 0.5. The velocity of the water going in the hose is 2. What's the velocity coming out? So I'm going to kind of sketch this. Okay, you have the wider hose going down to the narrower nozzle. Here the radius is 0.5 centimeters. Here the radius is, 2 centimeters. We know the velocity here is equal to 2 meters per second. And we want to know what the velocity over here is. So we have to find the radiuses. Now, I'm actually not going to convert because you're not going to need to, and I'll show you why in a second. Normally, I want my areas to be in meters squared, so I'd have to convert the 2 into meters squared. But I want you to see what happens. So area A, we'll call this section A over here, is equal to pi r squared, so it's equal to pi times 2 centimeters squared, gives me 4 pi centimeters squared. And the area at this end, the area at B, is going to equal pi times the radius of 1/2 squared, so that gives me pi over 4 centimeters squared. Now, my equation is A1V1 is A2V2. So the area over here is 4 pi centimeters squared times the velocity of 2 at the left end equals pi over 4 centimeters squared times the velocity here is what we're looking for. Now, the reason I knew I didn't need to convert them is because since I have area on both sides, it's going to cancel. So these units will cancel over here. And now this gives me 8 pi equals pi over 4 times v2. I can cancel the pi's. I would cross multiply, and I get v2 is 32 meters per second. So because it's narrower, it's going to be going a lot faster. Instead of going 2 meters per second, when it comes out of the hose, it's going 32 meters per second. Now, the next piece is Bernoulli's equation, and it's going to look kind of ugly. Okay, the way it's written on the reference table is P plus rho g h plus 1/2 rho v squared equals constant. Okay, I think they wrote it that way to save some space. I always write it this way: P1 plus rho g h1 plus 1/2 rho v1 squared equals P2 plus rho g h2 plus 1/2 rho v2 squared. It's really a conservation of energy problem. If you look at this term here looks like potential energy, but we've replaced the mass with rho, and this piece looks like kinetic energy. And you can handle it just like an energy problem. Pick 2 points, 1 and 2, find this here would be the total energy at point 1. It's going to equal the total energy at point 2. Make it like this is conservation of energy. So for this example, we have that at one end it has an area of 20 times 10 to the minus 6. And then the area at the other end is 5 times 10 to the minus 6. And then the velocity over here is going to be 2. And in part A, it's asking what is the velocity over here. So this is going back to it's going to be faster where it's narrower. The equation for that is A1 V1 is A2 V2. So I get 20 times 10 to the minus 6 times 2 equals 5 times 10 to the minus 6 times V2. I can cancel the times 10 to the minus 6's, and that gives me 40. 40 divided by 5 is 8, so V2 is 8 meters per second. So it's going faster at the narrower end. Now for part B, we want to find the pressure at the left end. It says it's open to the atmosphere at the right end. So over here, since it's open to the atmosphere, the pressure is 1 atmosphere because it's open. And we want to find the pressure here. Now, if this fluid is static, going back to Pascal's principle, if they're the same height, they're the same pressure. But now that it's fluid, that doesn't have to be true. Or now that it's flowing, it doesn't have to be true. Now, what is the pressure at the left end? Well, we're going to use Bernoulli's equation, and we're going to call this point 1, we're going to call this point 2. All right, so P1 plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V2 squared. Now, you look for, just like in conservation energy problems, roller coasters, whatever, you look for where things are equal or where things can be 0. There's no change in height here, so I can say H1 equals H2 equals 0, and then I don't have to worry about these terms here at all. So it simplifies it. Now, I'm looking for pressure 1 plus 1/2. The density, it's water flowing through there, so density is 1,000. We know that the velocity over here is 2 equals P2. The pressure is this side with 1 atmosphere. We have to remember it has to be in pascals, so 1 times 10 to the 5th pascals, plus 1/2, we have the density is 1,000, times the velocity at this end was 8. All right, now, This gives me P1 plus, that would be 4,000 divided by 2 is 2,000 equals, this is 100,000 plus gives me 64,000, 32,000. Okay, and when I solve this, I get P1 is equal to 130,000 pascals. One thing I want you to notice here, where it's faster at point 2, pressure was less. It was only 1 atmosphere or 100,000 pascals where it was faster. Where it was slower, okay, it was 130,000 pascals. So we'll make a note of that the pressure is lower where the velocity is faster. Okay, one example of that is like when you're in the shower. Okay, there's water running on the inside of the shower, so there's movement on that side. It's faster on the inside than on the outside. And if your shower curtain isn't weighted, the shower curtain will actually kind of swing in towards you. It's because the pressure where the water is moving is lower. Okay, so the shower curtain gets pushed in towards the side where the pressure is lower. The next page, we have another example. This is how airplanes create lift. So an airplane wing is shaped so the air flowing above it must travel farther and therefore faster. So if I think of it, the air over here is going like this. On this side, it's covering less distance, so it has to go faster on top. But it's going faster. Now, we're given here that the velocity up here is equal to 64 meters per second. We get down here that the velocity here is 52 meters per second. Okay, we're given that the area, we're going to use at some point, is 16 meters squared, and we're given that the density is 1.29. And then what is the difference in air pressure between the top and the bottom of the wing? These are moving, air is a moving fluid in this case, so we have to use Bernoulli's equation. So P1 plus rho g h1 plus 1/2 rho v1 squared equals P2 plus rho g h2 plus 1/2 rho v2 squared. Now, the difference in height above an airplane wing is kind of negligible. So just like the last problem, we can say h1 equals h2 equals 0. We want to find the difference in pressure. We don't know either one, so this will be, so we can cancel these. And then we'll say P1 plus 1/2, density was 1.29. Velocity below the wing, we'll use this, is 52 squared equals P2 plus 1/2 times 1.29 times 64 squared. So this gives me P1 plus 1744 equals P2 plus 2642. Now, I'm going to rearrange this because I want the difference in pressure. So P1 minus P2 equals 2642 minus 1744. And that gives me that the difference in pressure is 898 pascals. Now I found the difference in pressure from the top and the bottom. Remember, the top has a lower pressure because it's moving faster. If it has a lower pressure on the top, it's being pushed upward because the bottom is, the air on the bottom is pushing harder than the air on the top. So now, how do we find the force in part B? Well, if you remember, P is F over A, so therefore F equals P times A. The pressure is 898. And the area was 16 meters squared. And that gives me a force of 14,368. Incidentally, that's why in a tornado or a hurricane, the roofs get blown off of houses. I'm going to draw a picture. You have to draw it, but I want you to kind of see it. If I think of the roof on the house, all right, inside the house, the pressure is normal. Outside the house, since the air has velocity to it, okay, the pressure is going to be lower. So you have a little pressure pushing in and a bigger pressure pushing out, and it will actually blow the roof off. It's not that the wind is sneaking in under here and tearing it off. It's that the air inside the house is pushing harder than the air outside, so it pops the roof off. Now, I have an interesting problem here. When I did this problem the first time, I was very confused. Let me see what happens here. Let me show you what happens. The tube is open to the atmosphere at both ends. So I know the pressure here is 1 atmosphere because it's open, and I know the pressure here is 1 atmosphere. Okay? At the top end, the velocity is 1, and I want to know the velocity at the bottom. Okay? So again, it's a moving fluid, so I have to use Bernoulli's equation. So P1 plus rho g H1 plus 1/2 rho V1 squared is equal to P2 plus rho g H2 plus 1/2 rho V2 squared. Now, the pressures are the same, so I can cancel them. So pressure 1 and pressure 2 are gone. I'm going to call this point 1 and this point 2. Here the height is 0, and up here the height is 2 meters. So now I can start plugging in. It's water in the pipe. So I can use 1,000 for the density. So 1,000 times 10 times H1. H1 is 0. Plus 1/2 times 1,000 times V1 squared, because we're trying to find the velocity at the bottom, which we don't know, equals 1,000 times 10 times 2, height 2 was 2, plus 1/2 times 1,000 times 1 squared. So this goes away because the height is 0. This gives me 500 V1 squared equals, this is 20,000 plus 500. So 500 V1 squared equals 20,500. So then V1 is equal to 6.4 meters per second. And it makes sense that as the water falls from the top to the bottom, it's going to speed up. Here is the problem. By the equation of continuity, okay, that's the A1 B1 equals A2 B2. The velocities should be equal. Because the areas are equal. And I looked at that and I got really confused, and I started looking in books to try and figure this out, and I couldn't find it anywhere because these two equations, Bernoulli's equation and the equation of continuity, are giving me different answers. And I had trouble trying to figure out, they're both right, so what's going on here? It turns out that here's what's happening. And if you turn on a water faucet, you notice this. The water, as it pours out of the faucet, as it's going down, it starts to speed up. If it's going faster, it has to be narrower, and the stream actually narrows down. So what will happen is the stream of water narrows as it falls. So if I could see inside this pipe, what I would find is that the water doesn't fill up the entire pipe. It gets narrower as it goes down. So Now, by the equation of continuity, it's going to be going faster because it's narrower, and by Bernoulli's equation, which we just figured out, it's going to be going faster.